I mean, maybe we should get started, and other people, I imagine, will trickle in. So it's my great pleasure to introduce Yi Yang, who got his PhD in computer science from Northwestern, and started a faculty position after a postdoc at a business school. And just recently, in the last year or so, got tenure at the Hong Kong University of Science and Technology. In addition to publishing a bunch of business journal papers, which are necessary to advance in the business school, he also manages to publish a bunch of NLP stuff, and runs a sizable lab doing NLP and machine learning research. And he was just telling me that he is happy to be here because he wants feedback on AI, basically. Would love to hear, because he's in a business school, feels a little bit out of the loop, and would love to have us critique his work and suggest improvements we can think of from AI. So with that in mind, happy to have you start.
Yeah, thank you, Doug, for the very nice introduction. Yeah, I think I can skip the first slide. But yeah, I'm an associate professor at Hong Kong University of Science and Technology. Yeah, I've been in the B school. I'm still doing NLP stuff, machine learning related stuff, but more like applied this technique in the business context. To me, I think it's interesting because many of the most of the machine learning NLP people really don't care about like a specific application or downstream tasks like finance or law. That's a big bio NLP group, but the finance NLP group is kind of small. You know what I'm saying? So most of my research actually tackle this kind of question: how to adapt this well-established NLP method to some business problems. Yeah, I got my PhD from Northwestern. Doug is my advisor. Actually, when I heard that Doug left Northwestern and joined AI too, I feel like it's my bad, and I must be so bad being a PhD student. And Doug, I feel like, okay, so that's enough. I don't want to supervise any student anymore. So to just join, leave for the industry. Okay, or maybe it's Chandra's fault. I don't know. Okay, so today in today's talk, I'm going to talk about embedding models. So you guys must be expert in the embedding models. I'm going to talk about some works that I've been doing with these embedding models because I think this is a really cool field. So without going to the details, an embedding model today, specifically the textual embedding model. Okay, I'm focusing on textual embedding model. Embedding is just a vector, a high-dimensional vector. You pass this textual sequence into the embedding model, and you will get a high-dimensional vector. Okay. The magic, there's some floating numbers here. The magic of this embedding model is that these embeddings are supposedly to capture all the semantic information in that text sequence. And you can use very simple technique like cosine similarity to measure the similarity between two embeddings as a measure for the similarity of the original textual sequences. So, and the embedding model has a wide use of use cases in practice. Now we are excited about this generative AI, right? Large language model. But I personally feel like embedding models are actually the unsung heroes behind the screen. There's a lot of interesting applications that is motivated or can be built on top of this embedding models, such as like search and retrieval, RAG system, recommendation system, many more. Okay, so there's a wide use cases. And many of these companies are providing embedding models via API as their business model. For example, there's a lot of common big companies, OpenAI, Voyage, Cohere. They are providing the embedding model. Actually, to be honest with you, I think their model is good and it's very cheap. You look at how cheap this embedding model is. For 1 million token, they only charge you 2 cents. It's just unbeatable. It's so cheap. So their infrastructure must be so great. Okay. So what I'm saying is that there's many companies trying to monetize their embedding models via this API. And there's many. If we look at history, okay, we can see a very interesting patterns about this progress in embedding models back to the 1990s. There's the back-of-work model, there are n-grams models. When I started my PhD at Northwestern, Doug asked me to look at this topic modeling stuff, which is kind of one way to represent the text data, right? To learn a topic of vector. And then later we have this word-to vector, dot-to-vector kind of models. We have later have LSTM models, which is a sequential model. Then we have transformers, so we have BERT-based embedding models. Now, after ChatGPT is coming out, people are, pushing the frontier of embedding models via this LLM-based embedding model. So today, my talk will be focusing on the LLM-based embedding model because this is the state of the art. Okay, so today I'm going to talk about 3 works. The first thing I'm going to talk about how to build a general purpose embedding model. And the second, I'm going to talk about do we really need a domain-specific embedding model? And last, I'm going to talk about how to train a proprietary dataset-specific embedding models. So if you look at the work that I'm being presenting today, I will go from general purpose to more and more specific purpose embedding model. So 3 works. Any questions, feel free to ask, and I'm really looking forward for any critics. That's very helpful. Okay, so before I jump into the first work, I'm just giving a very quick introduction about embedding models. So for embedding models and for LLM-based embedding models, for this kind of model, we have a large language model in the middle. It's like a black box. You don't really know what's going on inside. Given a textual sequence, each token in the textual sequence will have a hidden state vector, and the last token also have a hidden state. Okay, also have a hidden state. So this is the most of the work actually. So there are different ways of getting embeddings out of a large language model. I will talk about that later, but the basic idea is that you give a textual sequence, go through multiple layers of transformer decoders, you will have some embeddings for each token. How do people benchmark, these embedding models? There's a dataset benchmark called MTEB dataset, which is short for Massive Text Embedding Benchmark. It's a widely used benchmark for embedding models. So you can see that companies actually many of the companies are benchmarking. They're like Cohere, Voyage, Salesforce. They're benchmarking their embedding models. Okay. This MTEB benchmark has 8 tasks covering a total of 58 datasets across 112 languages. But I think in the Hugging Face, they are keep extending these 58 data, so the benchmark is getting larger and larger. Okay, so this is state of art. Benchmark people use to evaluate the general purpose embedding model. Okay, so now we have some basic background information about the language model, basic embedding model, about the benchmark. Let's look at the first study, which I'm interested in. What are the effective LLM architectures for general purpose embedding model? So if you want to train embedding model, what's your training? How do you do that? Okay, so we just look at the literature. We just look at the common recipes for these embedding models. There are a lot of common things. First of all, most of these, almost all of them, LLM-based embedding models are based on LLM, right? Like open source LLM, Llama, Mistral, Q1. Those are the large language models. And the training objective for training this embedding model is contrastive learning. They use either triplet loss or use info NCE loss or whatever. Basically, they are trying to construct some contrastive objectives. And they are using publicly available QA data sets. Some work use ChatGPT generated data sets. For example, Microsoft have a model called E5 Mistral model, which they use to ChatGPT generate QA data sets for contrastive learning. And if you look at their training data set, so this is usually what it looks like. You have a query, you have a positive example, you have a negative example. For each query, you are training your embedding model in a way that the positive positive sentence instance embedding is closer to the query sentence embedding than to the negative sentence embedding. So that's basically the idea. So that's the training objective. In terms of tasks, they're trained on QA tasks, classification tasks, but they all constructed the training as positive, negative, contrastive learning methods. So these are common recipes. Okay, almost all the methods, all the models are using the same recipes. What are the difference? Well, the paper do have many different embedding models do have a lot of differences. In my opinion, some differences like the training data. Different models are trained on different training data. So if you look at their training data set, they are different size. Okay, like some models do not even tell you exactly the size of data, but basically they use different training data. And different embedding models, they are using different pooling and attention mechanism. Okay, so this makes me wonder, what are the effective training architecture for the LLM-based embedding model? Because many methods are claiming they are the state-of-the-art method, but they are training on a different data set. Okay, the data set may be the confounding factors driving the performance of the performance of the MTEB. So what I really want to know is, if I want to design the embedding model, should I use what kind of pooling and attention mechanism should I use? Okay, so let me just briefly talk about the pooling and attention. As I just said, these LLM-based embedding models, for each token, they will have an embedding, right? Each token will get embedded, will have a hidden state. So which, and the last token also have an embedding. Okay, so so this is LLM structure. Well, let's talk about attention. Attention, there are two ways. Either the causal attention, like the default attention used in the GPT, the decoder auto-regressive model. So let's use the causal attention as it is. However, people criticize the effectiveness of causal attention because the causal attention may they may argue that those tokens in the beginning of the sentences may bias the final embedding results. Okay, so the causal attention may be not the best way for getting because when you look at the total sequence, you want to have a global view. So people propose a bidirectional attention, which they modify the LLM's attention masks to allow tokens to attend to the preceding and following tokens at the inference time. So there are two ways of doing attention in building LLM-based embedding models. For pooling, as I said, there are multiple ways. The most simplest one is the last token pooling. Okay, people just assume that the last token, because the auto-regressive mechanism will encode everything in the sentences. Okay, so the OpenAI's embedding model, E5 mixture model, just use the simplest last token pooling. There are also some work using the mean pooling method because they think that the last token may not be as informative as every token. So they want to pool these hidden states together. So every word, the embedding will be put together. So that is called the mean pooling. And NVIDIA actually come up with a very interesting idea. They said, okay, why do we have to pool the embedding? Can we have another pooling layer, a trainable pooling layer? So the NV embed, which is the best performing model on MTEB. A few days, when I checked, last time I checked the benchmark, they actually propose a training layer. Okay, so they transform the last token's hidden state into a low dimensional space. Okay, so that being said, we have two attention mechanism and three pooling mechanisms that are commonly used in the literature. But when I start to think about the pooling, I'm just curious, why only the last layer for pooling? Okay, is it possible? Because there are so many layers in the LLM. Some layers may be, maybe the embeddings of different layers may encode different information. So what I did is that I did a very simple test. I tried to visualize the correlation between the hidden states of different layers. So this is a correlation heat map of the embeddings across the layers. So you can see that the layers that are far away actually have very little correlation, which means that they are kind of orthogonal to each other. They don't encode similar information. I also did a very simple test. I tried to apply these different layers embedding on the MTEB task and see the performance. So the last layers embedding is not always the best performed result. So some embeddings in the middle layers can actually perform better than the last layer. So which gave me this motivation, why only the last layer for pooling? So in this work, I'm proposing a multi-layer trainable pooling mechanism, which are trying to, capture the semantic information from all the layers in the LLM. So what I did here is that, well, to be honest with you, I don't know whether this will be effective. Okay, this is just an idea that why not all layers? So what I did is that the hidden state from LLM is to be taken, concatenated with a layer weight matrix, and pass through a cross attention mechanism to the final embedding. So these are all trainable parameters. So we have the weight matrix and the QKV weight matrix, which are trainable. The details are in the paper, but the basic idea is that we just want to follow NVIDIA's work by transforming the embeddings, the hidden state of all the layers into one hidden state, and leveraging the information from different layers. Does it make sense?
Sorry, so NVIDIA's work just used the last layer?
Last layer.
Okay.
Yeah, so last layer.
But you're taking input from all of the layers.
All the layers.
And learning a trainable.
The difference is that for NVIDIA's last layer, their input is every token's hidden state in the last layer. What I did is the last token's hidden state across the layers.
I see. Okay.
Yeah.
Got it.
Yeah. Okay.
Thanks.
So yeah. Okay. So but I don't know whether it will work. I did the evaluation. I want to benchmark the effective training strategy recipe for this LLM-based embedding. So what I did is that I pick up some combinations. So think about that. We have 2 attention 4 pooling, right? So 2 by 4 to be 8 combinations. But that's too much. I don't have enough training results for that. So what I did, I tried my best. I come up with the 5 combinations. Models are not considered the EOS last token pooling plus bidirectional attention, because if you really do the last token pooling, you don't need bidirectional attention. You see what I'm saying? Because the last token, if you do the last token pooling, supposedly the last token, the bidirectional attention is for all the mean pooling kind of stuff, not for the last token pooling. And I didn't consider mean pooling because the mean pooling has been shown to be not effective in the embedded paper. So what I did is that I just consider these 5 models. For example, if I want to know which are the most effective pooling methods, I can just look at the first 3 models because they are using the exact same attention. Okay, if I want to compare what will be the most effective method, pooling method under the bidirectional attention, I can only look at the model 4 to 5. So which gives me some fair comparison. Okay. By the way, all the models, 5 models, are trained on the exact same training data. You remember the table I showed earlier that they are using different data to train the model, so make the data could be the confounding factor. So in this case, I'm using the 1.4 million examples from the public available QA data set. So this size is comparable to this embedding data set used in previous work. And I want to say that there's no MTEB data sets used. I think it's very important because, surprise or not, many of these existing work, they are using the MTEB data set in their training data set. This is a embedded paper that literally say, look, the red boxes are the data sets that are in the MTEB data set, but also used for their training. They're literally using they really say that these are the data sets used for their training. Okay, so there might be some data contamination issues, which I do not want to happen. So I really want to have a fair, comparison. I use the initial 7B model. A training objective loss is a contractive loss. We also evaluate on the MTEB task. By the way, MTEB has 8 tasks, but actually I did not consider this 4 because for each of these 4 tasks, there are only very small number of data sets in the task, which does not allow me to do some statistical testing. Okay, so I only look at this retrieval, semantic textual similarity, classification, and clustering task. Okay, so the first result is about what is the optimal pooling design. Well, the result is kind of mixed. Okay, so this is SPS, classification, retrieval, clustering. If we use a causal attention, okay, so the first line, so first row, the row that is in gray color is the baseline, okay, base model. if we look at the causal, if we use causal attention, then using the trainable pooling layer can significantly improve the performance only on the STS task, not on the other 3 tasks. Okay. If we use the causal, but the difference is between trainable last layer NVIDIA's method and our method does not have any significant differences, which basically means that that's same. Your method does not work. Okay. My method doesn't work. If I were to use the bidirectional attention as the attention method, using my method, multiple layer trainable pooling can significantly improve the last layers across all dimensions, all tasks. Okay. What about the optimal attention mechanism? Okay. If we use the last layer trainable pooling, okay, you can see that, which is NVIDIA's method, using bidirectional attention can only significantly outperform causal attention at the retrieval task, but not at the clustering task, which kind of makes sense. Are you following the result? So let's say this is the trainable pooling, this is a multi-layer trainable pooling. That both trainable pooling, the bold phase number is with significant significance, only significant difference at the retrieval task, but not on the clustering task. So actually, sorry, using bidirectional attention actually significantly worse than use the causal attention, the simplest method, the default method for training.
Yeah, so why does that make sense?
It makes sense because when you do retrieval, some of the answer may be in the beginning of the sentences. So using bidirectional attention, which allow the vectors to pay attention to, the total sentence sequence to pay attention to early sequence, may better help. That's my hypothesis, okay? May better help the retrieval task. But for clustering, maybe like this, if 2 sentences are have semantic similarities, it doesn't really matter whether the words are in the beginning of the sentence or in the late end of the sentences. So, because when people criticize the causal attention, that the early tokens may bias the result, may bias the final result. Okay. Yeah, so bidirectional attention, which allows the final embedding to pay attention to all the tokens, may better than retrieval task. Since I think some of the answer may be in the beginning of the sentences, so that may benefit that task. But for clustering, maybe just the last token, the causal attention will just work as well. I don't know. So this is just an empirical finding. I'm trying to interpret the results. I haven't looked into much details about the data set, but yeah. Also, you may wonder what is optimal pooling plus attention design. Okay, so this is all the 5 models, 4 tasks. We do see some significant results here. However, what I want to say is that it's interesting to see that this trainable pooling, okay, and are significantly better than the last token pooling at STS and the retrieval task. But they're significantly worse at the classification and clustering task. I think the idea is similar to the previous, the explanation could be similar to the previous ones, that when you do STS and the retrieval, the early tokens may determine may be very important. For example, for STS, okay, this is a good movie, but I don't like it. So this is actually negative sentences, right? But if you only use the causal attention, which put a much importance on the later words, it may consider that as ignore the early sequences that this is a good movie, but I don't like it. So I think that may explain the performance differences. Let me put it this way: the tasks which require the model to understand early tokens, okay, such as STS or retrieval, may benefit from additional trainable pooling as well as the bidirectional attention. Okay.
Okay, I mean, it'd be interesting to actually test that hypothesis, maybe by trying to do these tasks using just the early tokens or something, or ablating
right.
early tokens.
Okay.
And then you could see just like based on how much, like how much the performance drops when you ablate the early tokens also correlate with the changes you see here.
Yeah.
That, I mean, that might test your, if that's what the hypothesis is.
I agree. Yeah.
I guess there's one, okay, first, well, this is a little bit off topic, but I want to respond to something you said earlier about how you hypothesized that I'd left Northwestern because of you. So it could not be further from the truth. Working with you was a sincere joy. But to go back to these results, I guess one thing this suggests is you might want a different embedding model.
Yeah.
Depending on the form of the downstream task.
That's true. You know, what I said in the paper is that given that most of the embedding models nowadays are using RAG, okay, with retrieval emphasized, so people may want to adopt more like a bidirectional attention as well as the trainable pooling. Because honestly speaking, I don't really think people would use embedding directly for classification. You know, it's very likely people will, like, say, fine-tune a BERT model, because most of the class, if you look at this MTEB and the classification task, like the new classification. If I were to do a classification task, I would just fine-tune a BERT rather than use this expensive LLM-based embedding model. Take it to his, and you know, because when you do this, you cannot tune the model for classification tasks. So yeah, that comment is well taken. The implication might be you need a different model for different tasks, and there's no one-size-fits-all winner. And I really want to. I think that this is one of the first studies that compare the attention and pooling design in a fair ground. Okay, because the data set is the same. Okay, they're controlled very well. Yeah, so there might be some trade-off between STS retrieval and classroom classifications. MTEB does everything together, putting together. The leaderboard might be a little bit not as informative as separately. Okay. So any other questions regarding the first work? Do you guys know, like, is that too obvious to you, like the pooling attention? Because look at the result. It seems like the very basic token pooling, last token pooling, and causal attention, the default one, just works as good. Well, there's some significant difference, but the margin is quite small. Okay, I'm not sure whether the GAN really worth it by using a more complex trainable pooling bidirectional design. Okay. Yes.
What are the metrics here in each of the columns? STS and classification, retrieval and clustering and stuff. Like, what is the?
They're different. They are different. Classification, I think, is like the AUC or accuracy something, or should be AUC. Should not be AUC because AUC is for binary. This should be accuracy. XPS, I think there's some like correlation something. They are different. They are different. So clustering, I think, clustering is also a funny one. Clustering, you know what? Clustering, the dataset that do have the ground truth. So actually, 20 news group is used in the clustering task. Each of the input they essentially have a label. So they basically compare whether the data set or the text message with the same label cluster together. But to answer your question, yeah, they have different metrics. I don't really remember the fine details. Yeah. Okay. So this is just empirical because I tried to build an embedding model, general purpose embedding model, and I really don't know which kind of architecture should I use. Should I use a bidirectional or should I use just mean pooling? So that's why it motivated me to try the first study. Okay. So the second one, I'm trying to look at the domain-specific embedding model. I want to know whether we need to build a domain-specific embedding because I'm actually in the business school. There's a lot of needs from my colleagues saying, okay, can we have a finance embedding model? Can we have a marketing embedding model? Can I have like accounting embedding model? I really don't know the answer whether we need it because there's some tension here. One thing is that it seems like a general purpose model is good enough. Those general purpose LLMs that have been trained on massive text data covering almost every domain. Can you name a domain that LLM's not good at? I don't know. Okay. But on the other hand, some of our early work show that advocate this domain-specific adaptation. I think this is a very famous, well-cited paper by AI2. Don't stop.
Pre-training.
Pre-training adaptation to another domain. Actually, this is me. We actually have a paper called FinBird, which adapts BERT to a finance domain. It's also cited very well in accounting journal. Yeah, and Bloomberg GPT, you must have heard about that. Bloomberg spent a lot of money to build their GPT model. And if also from a practical perspective, look at, so this is actually copied from Voyage, which is a startup companies. They are mostly selling embedding models. So this is their general embedding model, 2 cents per million token. Look at, they have some finance embedding and law embedding, and their price is 6 times higher than their general purpose embedding. Okay, so they charge more for the domain-specific embedding. So the question for me is that, do we really need domain-specific embedding? Because you see the tension here, right? Okay, good. So how do I answer this question? Well, I don't really know. So what I did is that I built a MTB dataset, but only focusing on finance domain. Okay, so in this test, I'm focusing on finance domain. So I'm trying to replicate MTEB. So I'm using all these 8 tasks. 7 different tasks, a total of 64 data sets. All of these data sets are finance data sets. Okay, they are using the financial NLP tasks. By the way, this data set is open source, so hopefully the people can use that for benchmarking. Okay, and let's just compare MTEB versus fine MTEB. If you look at their statistics, linguistic statistics, there are going to be some very significant differences between the financial data and the general text data. The sentence length is longer, token length is longer, syllables per token is longer, which means that, okay, maybe there's some domain complexity, okay, within financial MTEB, okay? So what I do, how do I, then I try to evaluate this open source embedding model. Sorry, not open source, this state-of-the-art general purpose embedding model, including OpenAI's embedding suite. Those are all the top performance model on the MTB leaderboard. Okay, so I use that embedding model, try the performance on the financial MTB. This is the MTB score. This is their full MTB score. So you see there's a significant drop by applying the general purpose model on the domain-specific embedding tasks. The performance drop is significant. Okay, it's very significant. It's funny that the one that have the least drop is the OpenAI's embedding model. The other models, I think, are heavily fine-tuned on the particular MTB dataset. Actually, suffers a lot from this, on this financial MTB. So we do see a performance drop, but doesn't mean that we do need a financial domain embedding model. Not necessarily, because as I just showed, these financial MTB dataset are inherently could be more difficult than the data set in MTB, right? So if you were to apply those models on a more, challenging data set, you may have an even higher drop. So that does not imply that you need a specific domain-specific embedding model. So what I do, so I want to control for the data set complexity, because as I said, the financial MTB may be inherently more complex than MTB. So I propose 4 ways for measuring the data set complexity. 3 are the traditional methods, like the information theory using Shannon entropy, readability, dependency distance, and also try the ChatGPT error rate, which I just converted this data set in a QA task into a QA questions and ask ChatGPT to answer a question. If ChatGPT gives me a wrong answer, I think this is a difficult, it's a complex, data set. Okay, so basically, I want to analyze the general purpose embedding model's performance while accounting for the data set complexity. So this is the result of subgroup analysis. We'll have 4 measures, 1, 2, 3, 4 different measures for data set complexity. I did a subgroup analysis where I look at the model performance, compare the financial MTB, the blue one, versus the MTB, the yellow one. This first column is the data set with low complexity. This is medium complexity. This is high complexity. The takeaway message from this figure is that under the same complexity level, financial MTB performance is worse than MTB performance on the same complexity level. Okay. I also do a more rigorous correlation analysis where I run this single regression model. The performance is the y, complexity is the x covariance. 4 columns, okay, given measures, and I look at their beta, which is the coefficient and the intercept. The results show that there's a negative beta for MTB and for financial MTB, which means that this general purpose model struggle with the domain-specific tasks that are exhibiting higher linguistic complexity. So the more complex the data set is, the worse performance general purpose embedding model is on data sets. And also the compare MTB and financial MTB, the intercept, you see that financial MTB has a lower intercept than MTB, which means that there's a significant performance gap, because if we control the same unit of complexity, the performance, the intercept actually on financial MTB is lower. Okay, so which means that there's a significant gap between the general purpose embedding model on MTB and on financial MTB. Okay, so this seems to imply that yes, you may want to train your domain-specific embedding model, which seems to be an obvious answer from some perspective. Oh yeah, also actually bench, do another study. So due to the time of interest, I'm going to skip this slide. Basically, the takeaway is that I think this is interesting to me, because I'm trying to, my colleague tried to approach me saying, can we try to, finance embedding model? I'm saying maybe it's not necessary, but now the results seem to convince me that maybe if I want to better understand the financial tech data, I need to use this technique to train a financial domain-specific embedding model. Okay. The third topic I want to briefly talk about is how do we train a proprietary dataset-specific embedding model. So it's not about domain; it's about a dataset. This actually comes from a very practical, motivation, because embedding model is widely used in RAG, right? Retrieval augmented generation. If we don't have good embedding model, we cannot have a good retrieval results. If you were to build a RAG, what are your options for your embedding model? You either go with the open source embedding model, or you go with the proprietary embedding models. Well, most of these embedding models are trained on general purpose, have a very limited domain specific. But for most of the companies, the data is proprietary. They do not want to give the data to the companies for various reasons. So why not build a proprietary data set specific embedding model? So this is some question that motivated me. So there's a lot of needs for building a proprietary dataset specific embedding model. Maybe this is a very niche domain that is very different from a common domain. Okay, the proprietary dataset cannot have very unique lingo and terms, etc., etc. So before I talk about the method, I just want to share some observation. Almost all these LLM-based embedding models are trained on the QA tasks with instructions. Okay, and those QA tasks are mostly based on the public available data set, which are manually labeled. However, for most of the real-world scenarios, like company-specific RAG system, the data is free text data. There's no label on that. How can you ask a company to spend a lot of money to annotate the QA data set? So I think this is a constraint, or maybe this is a realistic thing in practice, that most of the proprietary data is not labeled. So based on this observation, we propose a method called auto-embedding, which is a proprietary data set specific embedding model. So the idea is it looks like this. If you do not have label data set. How about we build some pseudo label? Okay, so let's say this is a proprietary data set a company has. We prompt GPT-4 to ask GPT-4 to come up with some questions based on, where the answer is in the data in the proprietary data set. And then, well, this can replace with the Llama 3 or other models if you are really worried about the privacy, have privacy concern about the data set. And then we use the classic, yet very good, old and yet good BM25 retrieval method. So basically, we are leveraging these questions to retrieve some answers from the proprietary data set. Remember, the BM25 only use the keyword matching, n-gram matching, so the quality may not be good. We leverage the top case retrieval, but the rank here may be noisy. Okay. However, we feel like this, although it's noisy, but the signal may still be there. Okay, because BM25 is still a very good retrieval model. Then we build some contrastive learning signals. So in this way, we treat the top 3 retrieved answer is the positive example, while the top 3 to 5 is a negative example. So this is more like a hard negative in the contrastive learning settings. Then we use the contrastive learning method. We train the LLM-based model, so we got a proprietary data set specific embedding model.
So the contrastive learning signal is just trying to basically trying to learn the BM25 ranking.
Similar, yes, you can say that.
Okay.
So the focal query here is the questions that generated by GPT-4.
Okay.
The positive example is the top 3 retrieved answers, the chunks. The negative is like top 3 to 5. But this top 3 and top 3 to 5 are all based on the BM25 retrieval results.
Okay. So, I mean, you could also go back to GPT there to get labels for relevance. That would be expensive.
Yeah, that'd be expensive. Yeah, and you have to put everything right to GPT-4, so that is not really possible. Basically, we are using BM25 as like a very noisy labeler, okay, to provide a very rough rankings about the relevance.
Okay.
That makes sense?
I mean, it kind of does, although I worry that, you'll learn a model that reverse engineers the BM25 function.
It could be.
But yeah, but that's not actually, you want a much stronger function than that, right?
Yeah, but the BM25, the point is that the contrastive learning is built on, is trained on the large language model, like Llama 7B or Mistral. They have its own capabilities, which may, maybe.
Even though it's a noisy training signal.
Yeah, even though it's a noisy training signal, still may pick up some signals there.
Okay. Interesting.
Yeah.
All right.
Because when I start this work, the pain point is that you don't have label data, you don't have QA. So we just build a QA using the BM25 retrieval technique. So let me show you the evaluation. We have 2 data sets here, the multi-hop RAG and the dragon ball. Actually, multi-hop RAG is the paper that I presented at COM last week.
Okay.
Yeah, so those are all the news based QA data set, and for the dragon ball is law, finance, and medical domain. Okay, and we use Q1 in the experiment reporting. But my student just reported me to a few days ago that the result on Llama and Mistral is also come out, and it's pretty consistent. But let me show you the results. Okay, on the multi-hop RAG as well on the dragon ball data set, we have our baseline is the BM25, and the Q1, which is the default large language model based embedding. Okay, this Q1 AE refers to auto embedding, which is refined on the multi-hop RAG dataset. Okay, so you can see that the performance score are just much higher, significantly higher than the default of vanilla Q1 as well as the BM25 result. But it's also worth noting that the BM25 is still very good. It's even better than the Q1 on multiple dimensions. So this is really good, strong baseline with BM25. So the signal may be noisy in a good way, I think. Okay. So the dragon ball dataset also shows a significant performance using Q1 embedding model. And I just told you that the result on Llama 3 as well on Mistral 8B is consistent. But I don't have didn't update my slides here. The improvement is consistent with the larger language model LLM. So this is 7B. The previous last slide result was 1.5B model. So this is 7B model. So you can see that performance of all the dimensions like hits, MAP are all much higher. So I mean, this is all the retrieval performance. Okay, retrieval performance much higher than the default methods. And the improvement is consistent with the re-rank use. So some in rank system, re-ranker is also a very commonly used component. But here, even we use the re-ranker model, the Q1AE auto embedding significantly outperform the baselines. Okay. So the takeaway message is that in many of the real-world scenarios where a company has its own proprietary data sets, instead of using general-purpose embedding model or domain-specific embedding model, they can totally build their own proprietary data sets that may be overfit to its own data in a good way, overfitting in a good way. Okay, so which can enhance the retrieval efficiency as well as the later generation effectiveness. Okay, so this is a I think it's a novel pipeline for building a proprietary data set specific embedding model that is effective, as shown by the improvement in performance as well as efficiency, because we don't have a human label in the loop. Just to summarize the three work that I did, I start with the general purpose embedding model, try to understand what is the good design architecture for the LLM. Then I talk about the domain-specific embedding model. Do we really need to go after a domain-specific embedding model? And last, I talk about building a proprietary data set specific embedding model. So that's the, I think I'm on time, a little bit over time, but yeah, that's my talk. Thank you. Any questions? Any critiques?
Thank you, Yi. Let's see. And yeah, any questions from other folks?
I have a naive question, which is, since you say that there is a cost of domain-specific embedding models, right? Is there a way to tell for which domain do you need to use this? Like for some domain that is like the performance is too close for the general purpose model.
Yeah, that would be a tough question to answer. First of all, how do you define domain? I feel like this is a very loose thing. I went to home and there's a talk about domain-specific model something, and turns out their domain is Wikipedia. Okay, not like the domain in my mind. I was talking about like finance, economics, healthcare, something like that. Okay, so let's say you want to say whether finance domain need an embedding model, law need an embedding model. I really, you have to benchmark on these domains, and maybe you need to go back to the, the linguistic patterns of each domain. So far, I don't think people have answer for that. I don't have answer for that. But people, at least from what I see, Voyage just build this law embedding, finance embedding, and healthcare embedding, and sell them at a higher price. Yeah.
So like, let's say if you just want to use it for a particular task or application, it might be just easier to try both general domain and look at the performance and see whether you work.
Yeah, that I'm not sure whether it would work because actually no. The slide that I missed actually talk about that. Yeah, this is the slide I missed. So actually we measure the correlation. Okay, so we have like 7 general purpose embedding model, right? They have their performance ranking on MTB and on financial MTB. I look at their correlation across the two domains, and the correlation is not significant, which means that the model that perform very well on general purpose tasks do not perform well on financial tasks. So they cannot actually just simply apply that to the general purpose embedding and see. The one that performs best will be work as well. So maybe that slide actually answer your question. Yeah.
Can you explain how you measured the inherent complexities of MTEB and FinMTEB again?
Okay, yeah, this is detailed, which I think I briefly talk about. Okay, so this is the dataset level complexity measure. It's the average of the complexity of each individual examples in the dataset. Let's take readability, for example. Readability has a formula. So there's a formula for measuring for example, the Gurney-Fox index has a formula. So you can actually measure the individual readability of each instances. And then I just average them across the examples to get the dataset level complexity. So you can say that MTEB have 58 datasets, right? So for each of the datasets, I have a complexity measure for it.
I see it. And how do you decide what's low, medium, and high?
That is just like a 3 quantile. So sorry, 3 buckets. You know what I'm saying? Like 1/3. I just can't. What's the word for that? Low, medium, high.
Yeah.
I just categorize this dataset into the low 1/3, the medium 1/3, and the high 1/3.
Okay, and
So it's a subgroup analysis. Yeah.
in every, so you took the union of the FinMTEB and the MTEB data sets, and then you took the thirds.
Yeah.
So this high category or like high complexity is like could have a different number of data sets from FinMTEB than
I
it
see.
does from MTEB.
You actually well, yeah, you said it right. You said it right. Well, actually, I don't remember exactly the details. I think maybe I'm wrong. So I normalize this the complexity. If you look at, I think the details is that. So we normalize the complexity into 0 to 1.
Okay.
And the from 0 to 1/3, the complexity will go to the low bucket. So the number of data sets in this may not be comparable.
Okay, got it.
But their complexity range is comparable.
Yeah.
Complexity range.
Yes, got it. Okay, thanks.
Yeah.
So those complexity measures in the previous slide did they have to do with just like raw language?
Yeah, mostly, yeah, like the information theory, like channel entropy, it's about the I think it's about like the raw language linguistic pattern. Readability definitely is about just the linguistics. Dependency distance is also the linguistic.
Okay.
Yeah, so it's very superficial level, I think.
Okay.
Not the semantic level. Yeah.
Does that necessarily translate to difficulty in performing retrieval and all of the other MTAB tasks also?
Difficulty?
So if these metrics say that FinMTEB, for instance, is more complex on average than MTAB or something like this, does that mean necessarily that evaluating a retriever would also have a harder time on FinMTEB than MTAB?
Yeah, I think so. This is more like complexity measure. I think I'm using the word difficulty and complexity interchangeably, right? Is that where the confusion from?
No, so I'm not sure. I don't know about the background of these techniques, honestly. So I don't know if like maybe I'm just ignorant, but like is it good to are these values representative of difficulty of the retrieval? Because what you're trying to do, so MTAB and FinMTAB are
it's not the downstream task performance level metrics.
Mhm.
It's mostly except the first one, because first one is about asking ChatGPT give the correct answer. So this may be related to difficulty. Those three is more like a linguistic complexity. Yeah, I'm trying to use this as a proxy for the difficulty, so that we can compare the general purpose model on these two different domains, accounting for the data set complexity. Does that make sense?
okay, but like, is it a good proxy? Do we have any evidence that it's a good proxy or a reasonable proxy?
I think the literature actually is funny that this afternoon I was actually reading a paper before I came. So that was a paper published in 2020 ACL or 2021 ACL. It's about leaderboard, because the leaderboard only report one number, but the different data sets may have different complexity level in that benchmark. So that paper was talking about, actually the Jordan's paper, it's talking about not all the tasks a data set are equally important. So you know what I'm saying. So I think their paper talk about some complexity measure. But when we work on this, I didn't know that paper. So I better check. But this is our proposed. You can argue that it may not capture what you want to capture. Could be. Yeah.
I guess given that you have a method for creating, data set specific embeddings. I mean, right? Maybe this analysis suggests that you do need a domain specific embedding.
Yeah.
I guess this is a question about future work. Are you planning to build one for finance?
Yes.
And then
Yes. So that's yeah. You're
okay.
right.
So then we can see what happens with that.
Okay.
But it does. I mean, I also think the correlation analysis you presented that when you take these general purpose embeddings and run them on the financial workload, you don't. The best models can change, or the ranking of the models can change a lot. So that also seems like a strong sign that
yes,
that you want a model that's tailored to this domain.
That's right. Yeah.
Okay. There's a hand. Aman, go ahead.
This is related to Doug's comment. So I was just wondering if you have tried evaluating any of the existing financial domain specific embeddings on FinMTEB, and if they're even competitive with the general purpose embeddings that you have.
The only finance domain embedding model that I'm aware of is Voyager embedding. There's no other open source financial embedding models available. I'm about to build one.
Okay.
And that Voyager embedding model is very expensive. I couldn't afford to try that. So I don't have the performance on financial MTB task.
Got it. Have you reached out to them by chance? I mean, if you gave them your benchmark, maybe.
Do you want to? Actually, there's a story behind it. Do you want a story?
Yes, I
just keep it off the table. Actually, when I work on this, a few months ago, their website says the coming soon, financial embedding coming soon, and I reached out them for the first try. So I reached out them saying that do you have like API that give us for free, like try? And they said, oh, we're still building that. They asked me this question: do you have any financial data set that we can use? So basically, I think what they're doing behind the scenes is they're actually like what we did here, collecting quite a lot of financial related data sets, making them like a QA data set, and it's a trend using the general recipe. You know what I mean, right? I'm really interested in comparing them because they're selling them at a very high price. Might be an opportunity.
You can ask like, sure, how much do you want to pay for it?
Yeah, but the trend is interesting. Showing that they're actually, looking like this domain-specific data sets. Yep. Yeah.
Well, great. I guess we're at time, but let's thank you again. Thank you very much.
Thank you.